Assalamu alaikum. My name is Moaaz Ahmad, and in this video, I will be talking about the line following robot project that was assigned to us by our professor Sir Umar Farooq and Sir Zargam Raza. This project was related to the course of microcontroller and embedded systems for mechatronics. So, first of all, what is a line following robot? A line following robot is an autonomous robot which follows either a black or white line depending upon the algorithm that you are using, and that line is drawn on the surface consisting of a contrasting color, which means that if you are using a black line that the robot is to follow, then the arena or the rest of the surface should be a contrasting color like white. And for white line, the color would be black. So the path line is predefined and visible with the black line on the white surface area in our case. The robot uses array of IR sensors to identify the line, thus assisting the robot to stay on the track. We were required to use a minimum of 5 sensors for our robot. So we decided to use 5 IR sensors for our robot to help it follow the line. The array of these sensors makes its movement precise and flexible. The robot is driven by DC motors that are attached to its wheels. In our case, there are two DC motors attached to each of the wheel, and we are using Arduino Mega to perform and implement algorithm. Moreover, we were also required to design our robot in such a way that it stops whenever an obstacle is placed in its path. So for detecting the obstacle, there were two options for us. Either we could use an ultrasonic sensor or we could use a simple IR sensor. So we used an IR sensor for obstacle detection along with SD card to store our path, and then after obstacle is detected, reread that path and follow it to the starting point. Moreover, we were also required to use an LCD to display information like voltage and current values that would be possible with the help of current and voltage sensors, and also display the speed of both of the motors. So for the speed, we used IR speed sensors that we will discuss in detail in the next sections. So let's get started. This is the block diagram for our project, and we can see that we have a total of 6 sensors as input, which involve the obstacle sensor along with the 5 IR sensors for line detection. One will be in the center, 2 on the left and 2 on the right. Then we have current and voltage sensor and encoder as input for our Arduino Mega. And Arduino Mega is giving output to 16 cross 2 LCD, and 16 cross 2 LCD is displaying information like encoder, current sensor and voltage sensor. The data that is obtained from these three components is being displayed on the LCD. As an LCD, we have motor driver as output, and motor driver is receiving signal from Arduino Mega and making sure that the motors are working properly, and then it is sending voltage to the left and right motors respectively. Then we have the SD card as output, as after each scenario after each scenario of these 5 IR sensors for line following, a value is being stored in the SD card, and SD card is storing it in a file in it, and then SD card is transferring that information to the Arduino Mega's input after an obstacle is detected, as we want our robot to follow the same path backward till it reached its initial point. So that's it from the block diagram. Now let's move forward to making the schematic for our project. So for the schematic design, I have already opened up the Proteus file for our project, and here we can see that we have our Arduino Mega right here, and this is our motor driver along with two DC motors. Here is our SD card that is attached to our Arduino Mega, and we have LCD 16 cross 2. Then we have a total of 6 IR sensors right here. These 5 out of the 6 will be used for line following mechanism, while this one right here will be used for obstacle detection, as it will be directed in the forward direction, and this will help us to detect obstacle in the path. Other than these basic components, we have our current and voltage sensors right here. We know that both current and voltage sensors are analog sensors. That's why both of these sensors are connected to analog pins, AD0 for voltage sensor and AD1 for current sensor. And the analog to digital conversion will be performed through our code that we will see in the later part of the video. And here we can see that we have used L29 3D motor driver for our project. And another thing that we were required to do, as I discussed in the previous section, that we were required to display the speed of the motors on the LCD. So for calculating speed, we are using IR speed sensors, which can also be referred to as encoder. So we have the IR speed sensors right here, and IR speed sensor is used to calculate speed depending upon the number of revolutions that a motor do in a second in a certain time period. So how an encoder works? So to visualize this, I will open a picture right here. Here we can see that each of our motors have a slotted disk attached to them, and these slotted disks have approximately 20 slots in them, and practically our IR speed sensor looks something like this. If I scroll down a bit, here we can see that this is our speed sensor, and we have a receiver and a transmitter. So that slotted wheel will be placed inside of this slot, and whenever a revolution passed, after a complete one revolution, it will have produced approximately 20 ticks. And these ticks will be stored in a variable in our code, and when a variable reaches a certain time period, or after a certain time period, like let's say after 1 second, we will use that value that will be stored in a variable for calculating the RPM of the RPM or RPS, revolutions per second, of our motor. And this is our IS sensor. It has a receiver and a transmitter right here, and we have our current sensor, voltage sensor, then we have our SD card module. SD card module is used in our project for reading data after an obstacle is detected, and then using that data to follow the path back to its initial point. And when it has not detected the obstacle, it will follow the path based on the line black line that will be already placed on the arena, and it will store that path into their SD card. So we have our 16 cross 2 LCD, and we have our motor driver, and then two wheels, Arduino Mega 2560, and then the most important component, robotic chassis. We are using two wheel chassis as I discussed earlier. That's why we will be using two DC motors and one motor driver. So I hope that you understand how IR speed sensor actually works. So schematic is done. Oh, one important part that our obstacle sensor is also a time sensitive task, as we want it to immediately stop as soon as it detects the obstacle. That's why this IR sensor for obstacle detection and our speed sensor, as both of them are time sensitive tasks, that's why both of them will be connected to the interrupt of our Arduino Mega. So let's move forward to the PCB layout. So this is our PCB design for our circuit, and we can see here that all of the components are placed at appropriate distance from each other. The most difficult part about this design was to design this Arduino pinout, as we had to use actual dimensions from our Arduino board and based our whole PCB design on that dimension, because our Arduino board was required to fit properly on these pins. Otherwise, it will not work properly, and there was a chance that it could damage our whole project, as it might cause any disturbance in voltage, etc. So for this, we used scale to measure our dimensions from the Arduino board, and then designed our whole Arduino layout based on these dimensions. And we have provided all of the pins right here. Even if they are not being used in our project, we still provided them right here so that it is easier for us to make any changes during our designing process. Like, first of all, we wanted to use the pin number 12, 11, 10, and 9 for our LCD, but later on, to use we decided to use pin number 13 instead of pin number 9. So then we it was helpful to us because we have already designed all of the pins for our Arduino board. So other than the Arduino board, we have our IR sensors right here. These five sensors are for line following, and then this one right here is for obstacle avoid. Then we have our voltage sensor and current sensor right here, and these are connected to analog pins right here and here. Other than these sensors, we have our potentiometer right here, and potentiometer in our case is used for controlling the contrast of the LCD, how much bright we want it to be. And we have our LCD, which is right here, and we can see here that our LCD is currently using the 4-bit communication mode, and it is connected to our Arduino at digital pins 13, 12, 11, and 10. And other than that, it has two more connections to our Arduino, which are enable and RS pin. which are used for making sure that the data is being sent from Arduino to LCD and it is properly recognized as a command or as data. Other than that, LCD has some other connections like VCC, ground, PWM, which is connected to this pin right here, is connected to our potentiometer right here, and then it has another pin which is RW pin, and it is connected to ground. And then at the 15 and 16 pin, we have the contrast voltage and ground connected, and 17 and 18 pin are useless as it was not possible for us to use 16 pins for our PCB design of LCD as they were not available in the Proteus. So other than these components, we have two major components right here, our SD card module, and SD card module has a total of 6 pins. Voltage and ground are two of them, and other four of them are MISO, MOSI, clock, and select. So these four pins are currently connected to 53, 52, 51, and 50 number digital pins. And other than these, we have our 5-volt extra voltage that will be provided to our circuit so that the voltage supply is proper. And then we have our encoder that is connected to an interrupt as we discussed in the previous section. And then we have a motor driver which will be internally connected to our Arduino and specific pins, but it will provide output to our actual motor driver that is connected to our DC motors to our robot chassis. While designing this PCB, we made sure to minimize the use of jumpers as much as possible because we wanted to optimize it to the extreme level. That's why we spent most of the time on this, and it took us approximately 12 to 15 days to make it work and to make it as feasible for us as possible. We faced difficulties while designing this layout, so that's why we consulted Sir Omar Farooq for guidance and we discussed with him our problems that we were facing during design, and he shared with us some guidance material like some previous PCB designs of Arduino related projects, and he allowed us to use that design as a reference, or he even allowed us to copy paste material from that file. So that file helped us a lot in our designing process as we were able to visualize how our PCB must look in the end and how a certain component will be placed and how they are all working together and connected to each other. So thank you to Sir Umar Farooq for that particular file, and we can see that we are currently using approximately 5 to 6 jumpers. That is the lowest number that we could achieve for our project. So that is from the PCB design, and let's move forward to our PCB etching and soldering, the hardware part of PCB. we decided to use a copper board for our PCB, and we know that the first thing we need to do for making a PCB board is to transfer this design right here to a copper board before all of the other processes like etching or drilling, etc. So first of all, we printed this design to a sticker paper, and with the help of iron, we transferred the design from the sticker paper to the copper board, and it looked something like this one right here. So after this board was achieved, and this was the result that we achieved after transferring the ink from the sticker paper to the board using iron. We then dipped this board in the FeCl3 ferric chloride solution for approximately 20 to 25 minutes, and this procedure was like something like this. And we can see here that the board is currently dipped and we are stirring the solution, and what it is doing is it is removing all of the copper from the board and leaving us the track lines only. And then we removed the track lines from the board, then this will give us something like this, that the proper connection lines that we can use to make a proper circuit and make connections between different pins. After this was achieved, we made sure that all of the connections are intact. So we used DMM to check the connectivity of all of these lines. And after we were sure that the PCB board was connected properly, then we proceeded with our component placement. But before the component placement, we needed to drill these holes in it. So we used a drill bit with a drill machine to drill these holes. So after drilling holes in it, we decided to do the soldering part. And for this, we used male headers for most of our connections, because for the Arduino, we were only going to use the male headers as Arduino Mega has the female headers on it. And on these headers, we placed all of the components. So our initial PCB looked something like this. We have our Arduino Mega right here, our SD card module, our voltage sensor, and this right here is connected to our current sensor. And we have our 6 pins for our IR sensors for obstacle and line following. And this one right here is for motor driver, and this one is for encoder. And here our potentiometer will be connected, and this one is for extra voltage. And right here we have the pins for LCD, which is not connected to the board currently, but we will see it in a little bit. So that's our PCB design, and that's it from the PCB section of the video. So let's move forward to the coding page of the project. Our robot was required to follow this logic right here, that when a certain scenario is being followed, it will follow the black line and move forward. But if all of the sensors involving the left sensors and right sensors and the sensor in the center all are on and all are on the black line, this means that the motors will stop and the robot will stay at its position. But if one of the sensor is on, then it will move in that sensor's direction, understanding that a black line is being detected in that direction. So to understand the whole logic behind our robot, let's move towards the truth table. This is a truth table for our robot, and we can see here that we have two sensors on the left, two sensors on the right, and one sensor in the center. And then we have another column for result. And these are the short acronyms for directions. S is equal to stop, F is equal to forward, L is for left, and R is for right. So we can see here that if all of the sensors are off, and similarly if all of the sensors are on, then the result is stop, which means that if the robot is on the white surface or totally on the black surface, then we want it to stop. But if one of the sensor on the right is on, either one of them or both of them are on, then we want it to move in the right direction. And for moving right, the left motor will be on and right motor will stay exactly where it is. And if only the center sensor is on, this is the only case where the forward direction will be followed. That if only the center sensor is on, then it will move forward. Otherwise, it will not move forward, and it will move in either of the direction, or it will stay intact. The next scenarios are as follows. If one of the sensor on the right is on, but the center sensor is also on, then it will again follow the right direction. And even if all of the sensors on the right and the center sensor is on, then it will still follow the right direction. Now for the left sensor, if one of the sensor on the left is on, then it will follow the left direction, and for moving left, the motor on the left will stay at its exact position while the right motor will move forward. But this scenario is tough, as if one of the sensor on each side, one on left and one on right, is on, or if the sensors on both of these sides are on, then it will not move at all. Because if both left and right sensors are on, then it means that it is detecting two black lines at the same time. Then it is not possible for our robot to make decisions, because making decision is part of a maze following report, because in that scenario we have to choose a priority for our board, that it will follow. In such a scenario, it will follow the left direction or it will follow the right direction. But in our simple line follower report, we do not have such option. So in our case, it will simply stop. And this scenario will apply even if both of the sensors on left and right are on. If one of each is on, or if one of each is on along with the center sensor. So we will look at it in a bit. And here we can see this one right here, this one, that left sensor is on, center sensor is on, and the extreme right sensor is also on, which means that the result will be stop. But if only the extreme left sensor is on, then it means it will follow the left direction. So same case followed right to the bottom. But all of these scenarios that we just discussed are only applicable if the sixth sensor, that is our obstacle sensor, is 0. And since the start of the program, it has not even gotten to 1 for a single time. And from the start to the moment, to this moment, if it has not changed its value from 0 to 1 even a single time, then all of these scenarios will be followed. But if it has changed its value to 1, then these scenarios will not be followed. Because after an obstacle is detected, which means that the value of obstacle sensor is changed, these scenarios become useless. As after the obstacle detection, we are required to read the path from the SD card and follow it back to our initial point. So that's the scenario that we have to follow. So let's move forward to our Arduino code to discuss this case in detail. So this is our code for our project, and first of all we included the LCD library. It is by default present in the Arduino IDE, and then we defined some constant integers for our LCD definition, which involved RS, enable, D4, D5, D6 and D7. All of these variables contained the pin number that we are going to use for our LCD. So on these pins, we defined and created an LCD object. And then we defined some other integers for our sensors, and for obstacle detection, we created another integer and we initialized it at 0. Then for our voltage sensor, we defined some basic variables like voltage pin, which will be A0, and V out, V in, R1, which is the resistance one, and R2 for our second resistance. Then we have the value is equal to 0, which will be the total value that will be displayed to the LCD. Then we have a float type variable called analog value and another float type variable called input voltage. Then we have current sensors and current pin, which is equal to A1, sensitivity is equal to 66, and that will be used for ADC conversion. And then we have the ADC value, which is equal to 0, and offset voltage is set to 2500. This is done so that we could remove any error from our value and get a more accurate value. Then we have the ADC voltage equal to 0 and current value is equal to 0. Both of these variables are of double type. Then we have another volatile integer, remember, is equal to 0, which will be used for remembering the path back to our program and making decisions on it. This variable will act as a boolean for distinguishing between whether the path has been remembered and the robot is ready to follow it, or it is still remembering the path. Then we have RPM as an integer, and then previous millis. Previous millis is previous millis will be very useful for our project, and especially for RPM and for IR speed sensors, as we want our speed sensor to give us a value after every 1000 milliseconds. So this previous milliseconds will act as a 1000 millisecond mark, and this will help us in that particular scenario. And then we have included our SD card libraries, spi.h, which is the connection, and then we have the sd.h, which is for SD card. Then we have created two files, variables file, and my file with double E. These two will help us for reading and writing to the SD card. And in the setup function, remember that the setup is a function that is initialized at the start of the program for once. And this program will be initialized only once and never again in the program. And this will be automatically initialized. We do not have to call it in some kind of main loop, etc. The first thing we do is lcd.begin. We initialize the lcd class and make an object of it, and we begin lcd 16 cross 2 since we are using the 16 cross 2 lcd. So we set up the lcd's numbers of column and rows. Then we have the pin mode, and we define A4 as input. This pin will not be used in our scenario. And then we have the pin mode 7, 8, 9 and 15 as output, and these pins will be connected to left and right motor respectively. And then we have 4, 5, 6, 16 and 17 number digital pins for our left, center and right sensors for our line following. Now for our object detection or obstacle detection, we are using an interrupt as we discussed in the previous sections. So for this, I will call the attach interrupt function, that is a predefined function in the Arduino IDE, and with it I will call the digital pin to interrupt, and I will pass the pin number that I'm targeting, which is digital pin 2, as digital pin 2 is equal to interrupt 0. And next thing I define is the function that I will be calling and the state I will be monitoring. So this line right here means that whenever the digital pin to interrupt 2, which means digital pin 2 is changed from 0 to 1, this function right here, obstacle detect, will be called. Same is the scenario with digital pin to interrupt 3, which is connected to our encoder, and for this we will also be monitoring the rising mode, and the function that will be called is count pulse. Now the next thing is to open the serial communication between the SD card and the Arduino. So to make it look more real and to help us in debugging and see if the SD card is connected to the motor driver, SD card is connected to the Arduino or not, we will be using this line right here, lcd.print serial check. Then we will delay it for 2 seconds, and then we will begin the serial communication at 9600. So then we will initialize a while loop while serial does not return true. We will wait for the serial port to connect, and unless the serial port is connected, it will remain stuck here, which means that either SD card is not connected or the SD card module is not connected. So after this loop has been escaped and the serial has returned true, which means the serial port is connected now, we will check whether the SD card is ready to work or not. So for this, if SD card dot begin at the pin number which is connected to our SD card, if this pin does not return true, then we will remain stuck here as long as this pin does not return true. So once we are done with that, we will open the file and note that only one file will be opened at a time. So for this, first of all, we will remove all of the previous files from the SD card. So we will use sd.remove and give the path of these files. So in our case will be path.text and check.text. And then at the start of the program, I will create a new variable. I will use this variable that I defined at the top, my file, and I will take it equal to st.open, and I will open the path.text file with permission file write. Now that I have permission to write into the path.text file, I will again close it so that I can reopen it in our while loop in the loop function. Now the count pulse function that we defined right here is provided right here. So whenever the count pulse function will be called, a variable called counter will be incremented by 1. And this will help us in our loop function, and we will see here that how the whole scenario of encoder works with each other. So just wait a bit till we get to this part. Next we have the turn left, turn right, forward and stop functions, and rotate function as well. All of these functions are targeted at directing the motors to work in a specific way. For the turn left, only one of the motor will be moving in the forward direction, and for the turn right, the left motor will be moving forward while right motor will stay same. For forward direction, both of the motors will be moving forward, and for stop, all of the motors will stay as it is. And for the rotate function, the left motor will be moving clockwise while right motor will be moving anti-clockwise, which will help us to rotate the robot around the center and rotate it 180 degree to the back direction. Now for the loop function, first thing we will do is, first of all we will take the voltage sensor reading. So I will call the value variable that we defined above, and I will take it equal to analog read voltage pin, and then I will call the vout variable, and I will multiply this value that was read from the analog pin, and I will multiply it by 5, which is our reference voltage, and I will divide it by 1024, which will convert it from analog to digital value, and this will help us in mapping. And then for Vin variable, I will take the V out and I will divide it by the total resistance R2 over R1 plus R2, and then I will send this value V in to the LCD. For the current sensor, I will call the ADC value variable that I defined above, and in it I will read the analog value from the current pin, which was A1, and then I will call the ADC voltage, and I will do the same procedure, ADC volt value divided by 1024 multiplied by 5000, and then current value will be equal to ADC voltage minus offset voltage, which we have already defined above, divided by sensitivity, which is also defined, and then we will display this value right here to the LCD with the ampere sign. And the next thing we will do is we will discuss how the encoder works. And for the encoder, we are using the M&ES function, which is a predefined function in the Arduino IDE. And what M&ES does is it gives us the number of milliseconds that have been passed since the start of the program. And we will apply an if condition here. If M&ES minus previous M&ES, which at the start of the program, if you remember, we set it to 0, is greater than 1000, which means that 1000 milliseconds have been passed, like 1 second has been passed, then we want it to take the RPM equal to counter divided by 20, which will give us the total number of revolutions done by motor in a second and we multiply it by 60, that will give us the total revolutions per minute, and thus we will get our RPM, and we will set our counter to 0 for our next cycle, and previous millis will be set to incremented value of 1000, and this cycle will keep on repeating itself as long as the program runs. Then we will exit the if condition and we will set cursor to 0th column and second row and first row, and then we will print the v is equal to v stands for velocity, and then we will print the RPM there, and after this we'll move on to our inputs. So we have used our ls2, ls1, cs, rs1, rs2 variables that we defined at the top, and we have stored the inputs from different pins into these variables. So we can see here that digital read 4 is equal to ls2, 5 is equal to ls1, 17 is equal to cs, 6 and 16 is equal to rs1 and rs2 respectively. Based on these inputs, our whole conditions will be defined. So first condition will be for the normal operation, which means if no obstacle is detected, then we want it to operate like this. So if no obstacle is detected, if obstacle detected is 0, which is the normal case as we have defined at the top, that obstacle detect variable is equal to 0, then we will call the myfile variable from the top and we will open the path.txt file in it with the permission to write. And next the thing next we will do next is we will use if conditions with each of our scenario. So if ls2 is equal to 0, ls1 is equal to 0 and cs1 is equal to 1 and both of right senses are 0, then if you remember, this is a scenario for our forward direction. So in this case, serial will be printing forward and forward will be displayed on the LCD, and forward will be written in the my file that we created here, path.txt. So to make sure that it remembers how much distance we cover in this direction, we will be using the millis for noting down our start and end time. So we will check c value is equal to 1, which is, let's say, our first case. So since this is our first case, we will move forward and we will skip this path right here, and we will simply move forward to forward, and which will cause our both motors to move in the anti-clockwise direction, thus making our report move in the forward direction. And the next thing we will do is we will set our cursor to 00 and our LCD will print forward, and our last value will be then set to 1 as it is exiting this if condition. And myfile.flush will cause our file to be saved, that all of the data that has been written to it will automatically be saved. Now if now in the next iteration, let's say this condition is being followed. Now in this scenario we can see that a lot of the cases have been defined. These are all of the cases separated by OR condition, and these are all the cases for our left motion. If any of these cases is true, then we want our robot to move in the left direction, which means that right motor will on and left motor will off. So what we will do here is we will change our C value to 2, and this time C value is not equal to last value. If you remember, last value was 1. So this time what we will do is we will clear the LCD and we will check if start is equal to 1. And if you remember, start is initialized each time we initialize it at the start. So if start is equal to 1, end time will be set to millis and total time will be equal to the difference of the end time and the start time. Start time was right here at this place. The start time was equal to millis, that it will give us the exact number of the time that has been passed since the start of the program, and end time will give us the time at that instant. And by finding out the difference between these two values, we can note down how much time it stayed in that particular direction. So using that time, we will store that time in the t time variable, and t time variable will be stored in timer array that will be called when we will be reading the data back from our SD card. So then it will exit this start, and then it will again set the start to 1. My file.print log will be left, and count will be incremented by 1, so that the next time the t time is stored, it is stored at the next value, and timer is equal to 0. Then we will turn left, and our right motor will on and our left motor will be off. LCD will print the left, and last value will be 2 this time, as we are exiting this if else condition. And my file will flush, so that all of the data that has been entered in the file is stored. So for the right, we will be calling the exact same pattern, and for the stop we will simply call the else condition, as there are more than 6 cases, and this line is not true. So for all of the else cases, we will simply call the C value, and we will follow the same pattern that we followed for all of the other cases. So now once the obstacle is detected, so before discussing the cases for obstacle detection, first let's move forward to the obstacle detection interrupt function, which is right here. And whenever this function will be called, first of all the LCD will display the term halt, and the next thing it will do is it will store the time that our robot was in the previous state, and it will store that time in the timer array. And next thing it will do is it will increase the value of obstacle detect variable to 1, so that we can differentiate between both of these cases in the loop function, and then it will stop all of the motors. So once obstacle detect is equal to 1, then we don't want any more interrupts. So no interrupts, and my file will open the st.open path.txt, but this time it will only have the read permission. And if remember is equal to 0, which is our default case, we will we will call the while loop to check whether the myfile.available function returns true or not, which means whether the path.txt file exists in the SD card or not. And then we will call the buffer list, and we will increment it at n, and in the n member of the buffer list we will read the string from the my file, and we will store it in the buffer. and then we will increment the n variable, and this process will go on as long as there are strings available in the file, and after the last string has been stored in the buffer list, my file will be closed and remember will be turned to 1, which means that all our path has been remembered in the buffer variable, buffer list, or we can simply say buffer array. So next thing we will do is we will check if remember is equal to 1, which now is true. This time my file will be equal to this file. We can simply say this file is for the check purpose that whether the whole path is being followed backward or not. So for this case, my file with double E is equal to st.open check.txt file write, and this time we will say for int j is equal to 0, j is less than 3, and j plus plus, we will turn both of the motors in the forward direction, one in the forward direction, one in the reverse direction, and it will rotate around its center, and we will print rotate on the LCD, and then after 1000 seconds we will stop it, and this loop will keep on moving as long for 3 times as long as the j variable is less than 3, and after this condition has been true we will simply exit this loop and move forward to while digital read 17 is not equal to 0, which means that while center sensor is not on the blank line, it will keep on rotating, and as soon as it is on the black line, it will exit this loop and it will stop. So we will now we are back to our original path, and we have rotated our robot 180-degree, and it is facing its back to the obstacle and its face is towards the path. And now we will call while n is greater than equal to 0. Now you remember that n is the variable that was used right here for our storage process, for our reminding process, and n was used for calling out different members of the buffer list or buffer array. So here we can see that while n is greater than equal to 0, int count will be equal to 0 and string check will be equal to buffer n, which means that buffer n, which means that member nth member of the buffer array will be stored in the check string, and based on that string we will check whether it has to move in the forward direction, either left, right, or it should stop. So we will print the text to the file, my file with double E, and that member will be printed to the list, to the file. So the next thing we will do is we will use the switch cases, and switch will be applied to the first member of the string check, which means the first character of the string. And based on that characters, we will say if the case s is used, which is for stop, my file dot print ln will be print line would be stop, and LCD will be cleared, and LCD will print all stop, which means in the reverse direction it is stopping, and it will stop. And the next thing it will do is it will wait for that time that was stored using the start and end time, and then By their difference, it was stored in the t time, and t time was stored in the timer array in our normal operation, and it will delay the process for that much time, and after it will break the case, and then we will again move to this loop start, and this time if the right, or if case r is true, which means the right direction was followed, then this time in the opposite direction it will be left. So LCD would print R right, which means it was right in the forward direction, but in the now it is following that right in the reverse direction. So it becomes left. That's why it is turning left, and it will be printed in the file, and then it will delay for that much time, and it will break. So that's how both of these cases will be followed again. And the reason behind this process right here, that we are multiplying the timer array by a specific number, the reason behind this is that delay was not following proper conditions based on data stored in the array. Thus, we had to multiply it with some value to get desired results. For multiplication with 1000, it gives a delay of 5.1 times of intended value. We used cases for this type of calculation, and for 8.5 cross 2 it gives nearest value of the result, so that's why we used 85 cross 2.5. And then we will set the default case to be break, and after each switch case a break, we will decrement the n value by 1, and it will move back to the top. So after the whole path has been followed, we will, and n has become less than 0, so remember will become 2, and my file will be closed, LCD will be cleared, and LCD will print done, and then it will stop as it has reached its initial position. So that's it from the code. Now let's move forward to actual working of the project, how it actually performed. So this is the robot following line, and if I play this video, we can see here that it is following the line as smoothly as possible, and it follows line for approximately 1 minute and 36 seconds continuously. And on the LCD, we can see here that if I move back a bit, and on the LCD we can see the status and the RPM along with the current and voltage value. So the major error that we faced for our during our first test was that our sensors were not properly aligned and not even properly optimized. So our report was seemed to facing this issue that it was giving priority to a certain direction. Uh, to be specific, it was giving priority to the right direction, but after identifying the issue, we changed the sensitivity to our sensors to different values, and then set our sensors in different conditions, because in the at the arena there was another major issue of the light, and light was affecting our results. That's why we used different scenarios, like by using the flashlight of the mobile for our robots run, and it gave us a pretty much good idea of what was the thing that was causing the issue for our robots working. So that was the working of the robot at line following. But now another important feature that we were required to make our project do was make it detect an obstacle and then rotate and follow the path backward. So for that part, I will move to the next video, and which is right here. So here we can see that as soon as the obstacle is placed in its path, it moves, it rotates, and it keeps following that path in the backward direction. So I think that this works properly and beyond expectation, I can even say that. And that's it from this working section. And if I have to say that, I and another thing that I want to say is I'm extremely grateful to Sarma Farouk and Sir Zargam Raza for helping us in this project and guiding us throughout the process. And this project helped us in getting to know our strengths and helped us in generating different ideas about how we can achieve different things and what to do in our FYP, which will be in the upcoming semester, and what we can achieve with these skills that we learn in our course, and how to implement these kind of skills in our different world tasks, real world tasks. And another application of this line following robot would be to use it as a mail delivery service within an office, that we can simply predefine a line for backline path at the front of each office, and we can define a T junction at that spot, and the mailman will simply place the mails on the top of this robot, and robot will keep moving toward the moving on the basis keep following the black line, and it will stop at each T junction, and T junction will be the respective manager's stop, and he will take his mails from the robot, and he will push the robot a step ahead so that it can keep following the black line again. So that's it from this project, and I hope that you learned something valuable. Till next time, Allah Hafiz.